Hi guys, and welcome to another teardown video. Today we're looking at Kailh BOX Inductive switches. Both these inductive switches and Hall effect ones are based on electromagnetism, but they operate on a completely different principle. I've also covered the Hall effect in a previous teardown video if you want to learn more details about it. The short version is that with Hall effect you use a sensor under each key to detect a transverse voltage perpendicular to a current by basically bending electrons off their direct path using a magnet. The Hall voltage depends on the magnetic strength, so in a fixed strength magnet is dependent on a magnet's proximity to the Hall sensor, and this is how these switches can sense how far they've been pressed. Induction is based on magnetic and electromotive forces interacting with each other. This can happen in two opposite directions. Putting current on a coil allows you to move magnetic things in and out of it, which is how solenoids operate, for example. You electrify a coil and then you can use it to create a piston. And the other way around works too. Moving a magnet through a metal coil induces a current into that coil. You can use this principle to detect when a magnetic material is moving through the coil, and hence it has applications in switching technology. Highly simplified, you connect the coil to a sensing assembly, and when you have a magnet moving through it, it can sense this motion and how far down it is. In the case of these switches, the inductive element is a cone-shaped aluminium spike, and I'll come back to why it's cone-shaped in a minute, but first you may be wondering how you can use a paramagnetic material like aluminium to work in an inductive switch which is based on magnetism. The answer is that while aluminium is not ferromagnetic, it is conductive, and under the influence of a changing magnetic field, such as from an AC-driven coil, so-called eddy currents are induced into the aluminium, which in turn oppose the coil's magnetic field. This phenomenon is called Lenz's law. This effect changes the coil's impedance, and this changes what the sensor detects. So basically you use the AC coils as a source of a time-varying magnetic field rather than a moving magnet in the slider. This method is called eddy current sensing, and one advantage of doing it like this is that the keyboard is capable of sensing where the keys are even when stationary. As induction only generates a signal if the magnetic field is moving, no induction would occur if the slider was the source of the magnetic field and it was held in place. By using AC to drive the coils, you instead get a constantly time-varying magnetic field, allowing the keyboard to sense how far down the key has been pressed even when it's not moving. As for the cone shape of the inductive element, it's tempting to think that this is done to make the switch analog capable, but it should be noted that the conical shape of the spike isn't strictly necessary to make the switch capable of gauging the push depth, as all it needs is a changing magnetic field, which you can still achieve with a rod-shaped inductive element. However, the conical shape does make it easier, as the cross-section of the cone inside the coil increases the further you press it down, which makes the effect progress non-linearly, and this in turn makes changes in the signal easier for the sensor to read, so to speak, and therefore it increases the sensitivity and resolution of the switch, especially in applications with height restrictions such as keyboards. Because inductive sensing assemblies can be made such that a whole sector of keys can be scanned at once rather than having to do so for each individual switch, you consume less power using an inductive system compared to a Hall effect one, which can make for a longer lasting battery when used in wireless applications. Though I'm not sure how different the drain rate would be in practice, as Hall effect sensing is normally not that power hungry to begin with. Inductive switches are also less sensitive to environmental factors such as temperature. Because most of the magic happens PCB side, the switch itself is extremely simple, consisting of just 5 parts: a top and bottom housing, a slider, coil spring, and the aluminium spike. The light pipe is not really part of the switch, it's meant to enhance the RGB and not necessary for the operation of the switch itself. That's it for this video, hope to see you in the next one. Bye guys.